Okay, in class on Friday we finished the derivation of the Navier-Stokes equations. The Navier-Stokes equations consist of three momentum equations plus mass conservation. And so what I'm basically writing here is the x component of the momentum equation. So we're looking at the conservation of u in response to forces. I'm not going to go back through the derivation here in the follow-up lecture, but I just want to kind of point out the different terms and help you to remind you what the terms represent. So, unlike in our control volume-based analysis, we put the accelerations on the left, and so this is essentially a sub x, where it's the x component of the acceleration. That means that we have the local acceleration and the convective accelerations. Where these terms arose from was through the flux terms in the momentum equation. So these were the momentum fluxes that became the convective acceleration terms. The local acceleration was, of course, the unsteadiness term. So in the original control volume-based analysis, what appears on the left-hand side of this equation was on the right-hand side of the control volume-based description. Now on the right-hand side, what we have is the sum of the forces. And this is then the force in the x direction divided by the fluid mass. We've divided by the mass so that the left-hand side has units of acceleration, the right-hand side has this 1 over rho dependence. What the terms represent on the right-hand side is in the first term is the normal stresses or the pressure forces. And so thinking about our little control volume, I'll sketch it in just a moment here. We have our cube of fluid that we're tracking. The normal stresses in the x direction would be the pressure forces acting on the two faces, normal to the surface. So we have pressure times area acting left and right. The last three terms here are the shear stresses. And the shear stresses in this result are due to the viscous dependence, and that's where the viscosity arises from the mu over rho factor. Now the shear stresses in our sketch would be acting on the top and the bottom, for example. And so we'd have the shear stresses tau times area, where tau is equal to mu du dz. That's what then becomes each of these three terms. And so this is just in the z direction, so that becomes the last term. The front and the back becomes the center term, and the left and the right becomes the first. So in the end, all the Navier-Stokes equation, the momentum equations represent is F equals ma, where we've done this full accounting for normal stresses, shear stresses, and then the accelerations on the left. Now, as I noted near the end of lecture on Friday, the variables that are unknown in this equation would be the velocities, so u, v, w, and the pressure p. So we need one more equation to close the system out. So how do we get the fourth equation? So we have three momentum equations in x, y, and z, and then we have mass conservation. And mass conservation has the form du dx plus dv dy plus dw dz equals 0. Now note, in all of the development on this follow-up lecture, I'm using, as you see in the upper left here, I'm using that the velocity is defined as u vw as opposed to vx, vy, vz. A little inconsistent with the lecture in class where I use subscripts. A little cleaner to go without subscripts, and so I used u vw here. In the end, what we have is four equations in four unknowns. We have the three momentum equations, we have mass conservation, and together that helps us define the three velocity components in pressure.